Hey everyone, welcome to another session of Ceerazzledazzle Physics. In today's session, guys, we're going to be doing a full GCSE Physics past paper. Today we're going to be looking at AQA GCSE Physics 2021 Higher Tier Paper 2. Obviously, make sure you've tried the paper yourself under time conditions and then watch this video. There's no point watching me do it, you've got to struggle yourself, and obviously you can just use this video to improve your exam technique and look at my thought process when I'm tackling the questions. Okay, let's get straight into it. Number 1. The thinking distance and braking distance for a car vary with the speed of the car. Explain the effect of two other factors on the braking distance of the car. Alright, so the first one that pops to my mind is going to be the condition of the tyres. So let's down condition of the tyres over here, condition of the tyres, and if they are worn out, so if they are worn, therefore there's going to be a reduced amount of friction, and therefore, if there's a reduced amount of friction, therefore the braking distance will increase. Therefore, braking distance will increase. Braking distance will increase. Right, so look, in this question, you've got to talk about the factor and the effect upon the braking distance. So we've done one of them. Let's try another one. I'm also going to talk about the condition of the road. So let's say if it's wet or icy, if it's a wet or icy road, therefore, there's also going to be a reduced amount of friction. There's a reduced amount of friction. And if there's a reduced amount of friction, therefore the braking distance will increase. Braking distance will increase. Okay, and obviously check with the mark scheme itself. There's some more examples that you can actually use, but these are the two ones I'm using today. Question 1.2. Which equation links acceleration, mass and force? F is equal to ma. It's the first one over here. Next one, calculate the deceleration of the car. So we're going to go F is equal to ma. The acceleration is equal to F divided by m. So therefore it's going to be 7200 newtons divided by 1600 kilograms. I'm going to get my answer of 4.5 meters per second squared. Easy stuff. 1.4. Figure 1 shows how the thinking distance and braking distance for a car vary with the speed of the car. So as you can see, we've got two lines here, one for thinking distance, one for the braking distance. Thinking distance goes up in a linear format, braking distance at a curve here. Right, and that's the speed in kilometers per hour. First question, determine the stopping distance of the car when traveling at 80 kilometers. Right, well hopefully you can remember that the stopping distance, so if we have the stopping distance, it's going to be equal to the addition of the braking distance plus the thinking distance, Okay, so all I'm going to do is I'm going to read off the thinking distance and the braking distance at 80 kilometers per hour. So let's put a dot here and put a dot there. So at 80 kilometers per hour, it's going to be 15 meters. And at 80 kilometers per hour for the braking distance, we are getting 38 meters. Therefore, the stopping distance is equal to the addition of them both. So it's equal to 15 meters plus 38. I'm going to get the answer of 53 meters. There we go, 53 meters over here. There we go, 15 plus 38 equals to 53 meters. Easy stuff. 1.5, which equation links pressure, area? So we know that pressure is equal to force divided by area, 1 mark. Next question over here, when the brake pedal is pressed, the force of 60 newtons applied to the piston. The pressure in the brake fluid is 120,000 PA. Calculate the surface area. Right, P is equal to F divided by A. A is therefore equal to F divided by P. The value of F is going to be 60 newtons divided by the pressure of 120,000 Pascal. Over here, I'm getting the area of 0.0005 over here, but it says give my answer in standard form, so I'm going to shift the naught, so once, twice, third, fourth, so it's 5 times by 10 to the minus 4. And look at my units. This equation, when we use this equation, force was in newtons, pressure's in Pascal, the area is going to be in meters squared, so 5 times by 10 to the minus 4 meters squared over here. That's my answer. So 5 times by 10 to the minus 4 meters squared. Figure 3 shows a child on a playground toy. The springs have elastically deformed. Explain what is meant by elastically deformed. If it's elastically deformed, basically it means that the spring will no longer return back to its original position. So after you've stretched it, when you remove the force, it will no longer return back to its original position. There we go, guys. For 2 marks, the spring no longer returns to original length when force is removed. When the force is removed. A student investigated the relationship between the force applied to a spring and extension of the spring. Figure 4 shows the results. We've got force on the y-axis, extension on the x-axis. Right, so that's our graph. Let's see what the question is. Describe a method the student could use to obtain the results given in Figure 4. You should include a risk assessment for one hazard in this investigation. Your answer may include a diagram. Right, you should have the clamp stand out over here. So here's you should have a clamp stand out. Here's our spring of original length L. And then you're going to add a mass to it, the spring over here, and look, it extends. Now there's a force acting downwards, yes, because there's a mass attached to the end of the spring, and this is the final length, lowercase f is the final length here. Right, if you want to work at the extension is going to be equal to the final length minus the initial length here. That's how I'm going to calculate the extension. And look, I've got clamp stand, I've got the spring, that's all I need, and the masses as well. Right, so describe a method, so we need to tell them what to do. So number 1, it's going to be set up clamp stand and suspend a spring. And then the second thing I'm going to be doing is going to be using a ruler, measure original length of the spring. And then 3, it's going to be, I'm going to add a mass to the end of the spring. And obviously we've added a mass to the end of the spring. And then we're going to calculate the force. Don't forget, that's the mass. To calculate the force, I'm going to times it by gravity to work out the force here. 4, it's going to be multiply mass by gravity to work out the force. And some of you might forget that the force which is going to be pulling down, this force here is the weight here. So that is going to be equal to the weight. So the force pulling down is equal to the weight, which is the mass times by gravity. That's the reason why I multiplied the mass by the gravity to work out the force. And that's what we're going to do. And then the next one is going to be, so we keep adding the masses on top, and obviously it's going to stretch out. And 5, guys, we have to measure the final length. It's going to be then measure final length of the spring. And last of all, to calculate extension, so calculate extension by subtracting original length from final length. And 7, it's going to be repeat but add more masses. Okay, but in the question, guys, it also asks about a risk assessment. So using spring, obviously the spring can bounce off and maybe hit you in the eye. So you can wear goggles to stop the spring from bouncing off and hitting you. So wear goggles in case spring bounces off. Excellent stuff here. 2.3, which equation links extension, force, and spring constant K? So it's going to be F is equal to spring constant times by extension over here. Next one, figure 4 is repeated below, force in newtons, extension in meters. Determine the spring constant of the spring. Right, spring constant, we can use the equation that they gave us. So let's pick this point over here, it's the easiest to read out. So we know that the force here is going to be 4 newtons. Force is equal to 4 newtons. The extension here is going to be 0.1 meters. Therefore, we can now plug it in to work out the value of K. F is equal to K times by E. K is equal to F divided by E. So therefore, it's equal to 4 newtons divided by 0.1 is equal to 40 newtons per meter. Easy stuff. 2.5. The student concluded the extension of the spring is directly proportional to the force applied to the spring. Describe how figure 4 supports this student's conclusion. Right, so you know it's directly proportional because it's a straight line, yes, straight diagonal line, and it goes through the origin. So that's 2 reasons. There we go, straight linear line and goes through the origin, everyone. 2.6. The student repeated the investigation using a different spring with spring constant 13 newtons per meter. Calculate the elastic potential energy stored. Right, use the physics equation sheet. So E is equal to 1/2 K times by E squared. So the energy is equal to 1/2 the value of K, 13 times by 20 centimeters. You don't like that, must convert to meters, 0.2 squared. The energy is equal to 0.26 joules. Next question, question 3. A main sequence star in a distant galaxy is the same size and mass of the Sun. Explain why the star is stable when it is in the main sequence stage of its life cycle. Right, in the main sequence life cycle, there's a balancing out of the forces. gravity is pulling it inwards, so gravity is pulling it inwards, and the energy, which is the force from the fusion, is pushing outwards. So you have a balance point between these forces here. So you have to talk about the gravitational force pushing inwards and the force due to the fusion pushing outwards are balanced. Excellent stuff here. So you get 1 mark for talking about the forces. So this is 1 mark, this bit over there, these 2 bits of the forces. And then talk about the forces being balanced is the last mark here. 3.2, describe what will happen to the star between the main sequence stage and the end of the star's life cycle. Well, this star is like the sun, so therefore it will, first of all, it will expand to become a red giant. So it expands to become red giant, and then afterwards it's going to collapse to become a white dwarf, and then last of all, guys, it's going to then, after it collapses to become a white dwarf, finally it will cool down to become a black dwarf. Superb stuff. So there we go, cools down to become a black dwarf. Figure 5 shows how the speed of the galaxies moving away from the Earth varies with the distance of the galaxies from Earth. Which galaxy would show the smallest observed change in the wavelength of the visible light? Which one is it? So look, speed and distance away. Which one's going to obviously have the smallest change in wavelength? Well, the smallest change of wavelength means that it's going to experience the smallest amount of redshift. So it's going to be moving the slowest and it's going to be closest towards us. So it's going to be A over here. So A, the reason why is going to be, you could say it's moving the slowest, so it's the slowest or closest to us. Either of those answers are acceptable here. So slowest or closest to us. Figure 4, lenses are used to form images of objects. Figure 6 shows how a concave lens forms an image of an object. The image of the object is upright. Okay, so it's upright here. Give 2 other words that describe the image. Right, so first of all, it's a virtual image because we've extrapolated the lines backwards. So it's virtual and it's going to be smaller than before. So we're going to say it's diminished. So it's virtual and diminished. 4.2, figure 7 shows an object near to a convex lens. Complete the ray diagram to show how the image is formed. Okay, right, so obviously I'm doing this on the screen, but you've got to be able to do this using pen and paper, yes? So obviously you draw your first line from the top of the object through the center of the lens over here. That's your first line over here. You draw another line going horizontally across. Don't forget, this is the next line you draw. It's going horizontally across over here, and it will hit the lens, but as it hits the lens, it will then start to go through the focal point. So we're just going to extend that line. So look, it's going to then go through the focal point. That's my second line over here. And then from here, everyone, you might be wondering where the image is formed. You've got to extrapolate both those lines backwards, and where they meet, that is going to be where the image is formed. So there, I've done one of them over here. I'll do it again. So there we go. There we go, guys. It's been done. It's over here right now. Then let's just draw it in now. So the image is formed when both of these meet over here. So it goes all the way down. Use a ruler when you're doing this in real life. This is the image over here. Excellent stuff. Draw the arrows on the diagram as well. So there we go. We're finished with this. It's 3 marks. Easy stuff. Next one. The position of an image formed by the convex lens varies with the distance between the object and the lens. Figure 8 shows the results of a student's investigation using a convex lens. Describe how the distance of the image, so this one, decreases as the distance between the object and the lens increases. Right, so what's going to happen to the distance of the image from the lens? Okay, so look. Between 3 and 4, this distance here, it drops down from there to there. So look, it's dropping down 3 to 2.4. It's 0.6 change between these 2 points. But then further on, the greater the distance, so look, at the larger distances, the drop is much smaller. There we go. So look, the drop is much smaller between there and there. It's much smaller here. Okay, so you can say that there is a greater decrease in image distance. Yeah, in this quantity, in image distance, for smaller distances between the object and the lens. I hope that makes sense. Yes, so look, there's a bigger change for the small distances compared to when it's a large distance. There's less of a change here occurring. 4.4. The student measured the distance from the image to the lens 4 times. The distance between the object and the lens did not change. The 4 measurements from the image to the lens were 1.9, 1.7, 2.2, and 1.4. Calculate the uncertainty. The uncertainty is simply equal to the maximum value minus the minimum value divided by 2. So therefore it's going to be 2.2 minus 1.4 divided by 2. I'm going to get the answer of 0.4 centimeters, plus or minus 0.4 centimeters. 4.5. Figure 9 shows a spotlight containing a convex lens. A red filter is placed in front of the spotlight. The spotlight is directed at a blue object. Right, so don't forget the red filter only allows red light to pass through. So why is the ball appearing black? So first of all, red filter allows only red light to pass through. And then when it hits the blue ball will absorb all the red light. And therefore blue ball absorbs all red light. As it absorbs all the red light, obviously nothing can be reflected back by the blue ball. So there's nothing reflected back by the blue ball. Easy stuff. Don't forget that the blue ball can only reflect blue light. And obviously red hits it, so it can't reflect that. Question 5. An ultraviolet is a type of electromagnetic wave. Give one use of ultraviolet. Detecting forgery. Or you can say sunbeds. Yeah, sunbeds for tanning. Yes. For tanning, yes, people get tans, yeah, for tanning. Next one, an ultraviolet wave has a wavelength of 300 nanometers. Which of the following is equal to that? Right, 300 nanometers, nano means times 10 to the minus 9. So 300 times by 10 to the minus 9 is the same as 3 times 10 to the minus 7. The speed of an ultraviolet wave is 3 times by 10 to the 8. Calculate the frequency of the ultraviolet wave. Right, so now the frequencies, let's do this. So V is equal to F times by lambda, yes? Frequency is equal to V divided by lambda. It's equal to 3 times by 10 to the 8 divided by the wavelength, 3 times by 10 to the minus 7 from before. Over here, we are going to get the answer of 1 times by 10 to the power of 15. Figure 5.4. Table 1 gives the wavelength of an ultraviolet wave and 3 other electromagnetic waves. So look, we've got an increasing wavelength here. So the wavelength is increasing. So lambda is increasing over here. And therefore the frequency is decreasing. Frequency is going to decrease. Right, so the EM spectrum is radio waves, microwaves, infrared radiation, visible light, ultraviolet, X-rays, gamma rays. Right, so this one over here has the highest frequency, high frequency, and therefore the lowest wavelength. Alright, so X-rays, we can see X-rays will have the lowest wavelength. Yes, X-rays have the lowest wavelength. In the spectrum over here it has the lowest wavelength, so therefore out of all of these it's going to be E. E has the lowest wavelength. That's the reason why it's going to be X-rays here. Right, G has the longest wavelength. So the longer the wavelength, therefore the lower the frequency. So which one's going to have the lowest frequency out of these? It's infrared. And the next one, it's going to be in between, right bang in between, it's going to be visible light over here. 5.5. Electromagnetic waves are transverse. Some other types of waves are longitudinal. Describe the difference between transverse and longitudinal waves. So, oscillations are at 90 degrees to the direction of the energy in a transverse wave. And in a longitudinal wave, the oscillations are parallel to the direction of energy transfer. Yes, it's all about the oscillations here. So in transverse waves, don't forget they're moving up and down, the energy is going across. In longitudinal waves, they're moving left and right, and the energy is also going left and right here. Figure 6. A student demonstrated some features of the waves using a ripple tank. Figure 10 shows the ripple tank. The student measured the time taken for 10 wavefronts to pass the mark. The teacher repeated the experiment 3 times and calculated the mean. What is the advantage of repeating experiments and calculating a mean? It's because you will simply reduce random errors. Yes, you reduce the random errors here. The teacher's measurements for the time taken for 10 wavefronts to pass the mark were 8.4, 7.8 and 8.1. Calculate the mean frequency of the wave. Right, first of all we need to calculate the mean. So the mean is equal to 8.4 plus 7.8 plus 8.1. I divide that by 3. I'm going to get the value of 8.1 seconds over here. That's the mean right now. Now if I want to work at the frequency, we know that the frequency is 1 over the time period, but we don't have the time period. I know it's 8.1 seconds for 10 waves. So how long does it take me for one wave? So if 8.1 seconds is going to be 10 waves, one wave is going to be 0.81 seconds. So one wave is 0.81 seconds. So let's throw that into there now. So now we've got this 1 divided by 0.81. We're going to get the answer of 1.2345 over here. But to two significant figures, it's 1.2 hertz. 6.3. In a different investigation, the teacher wanted to determine the speed of water waves in the ripple tank. The teacher did not measure the wavelength of the wave. How could you determine the speed of the wave? Well, hopefully we know that we can use speed is equal to distance divided by time. So maybe you can pick the distance of the ripple tank. So we can measure the distance of the ripple tank. So measure distance of the ripple tank with a meter ruler. And now we've done that, we've measured it out over here. We can time how long it takes for maybe a wave to travel that distance. And obviously we've got to talk about using a stopwatch. Yes, using a stopwatch. And then finally we're going to use the formula speed is equal to distance over time. There we go, use the formula speed is equal to distance over time. Question 7. A figure 11 shows a cyclist riding a bicycle. Force A causes the bicycle to accelerate forwards. What name is given to force A? Right, so this is going to be friction, everyone. Don't forget it's friction because you have to push off, and that's the reason why. So it's going to be friction. Figure 12 shows how the velocity of the cyclist changes during a short journey. So there we go, velocity over here. There's point Y, point Z. Determine the distance travelled by the cyclist between Y and Z. Between Y and Z, right, between Y and Z, the distance travelled is the area under that bit here. So we can work out the area of maybe this square and the area of the triangle and add them both together. So let's do the area of the square. So this value is going to be 5.4 at the top. We know it's 20 over here. This is 20 over here. And this one is also 20 over here. This is 20 over here. It's 5.4 at the top as well. So it's the area of rectangle plus the area of triangle. And that's going to be equal to the distance travelled. This is equal to the distance over here. So the area of the rectangle is going to be 5.4 times by 20. And the area of the triangle plus half times by the base times by height. Half times by the base, which is 20, times by the height, 5.4. Yes, look at that triangle. Half times by 20 times by 5.4. That will be equal to the distance. So therefore, that's going to be equal to 108 plus 54. Therefore, I'm getting the answer of 162 meters. 162 meters. 7.3. Figure 13 shows the gears on the bicycle. Describe how the force on the pedal causes a moment about the rear axle. Right, when you push down here, it causes a moment upon the pedal axle. So number one, force on pedal causes a moment on pedal axle. And now this moment creates a force on the chain. So this creates a force on the chain, and which obviously then causes a moment upon the rear axle, which causes moment on rear axle. Excellent stuff here. Figure 14 shows a different cyclist towing a trailer. The speed of the cyclist and the trailer increases uniformly from 0 to 2.4 meters per second. The cyclist travelled 0.018 kilometers while accelerating. Calculate the initial acceleration of the cyclist. Right, so v squared minus u squared is equal to 2as. That's the formula we're going to use. So therefore, a is equal to v squared minus u squared divided by 2s. The final velocity is 2.4. I've got to square it, minus 0 squared, divided by 2 times by, and I must convert this into meters, so which is going to be 18 meters. 2 times by 18 over here. 2.4 squared minus 0 squared, divided by 2 times by 18. I'm getting 0.16 meters per second squared. That's my answer. 7.5. The resultant force on the tow bar of the trailer has a horizontal component and a vertical component. The horizontal force is 200 newtons. The vertical force is 75. Determine the magnitude and direction of the resultant force on the tow bar. Right, okay, so first of all, look at that tow bar over here. So over here, it's going upwards. So I know the forces is going to be going across, then up here. You've got to use a scale diagram. So when you're drawing this, you've got to recognize how many boxes will you need to represent 200 newtons. I'm thinking, let's say this much right now is roughly 200 newtons. That's 200 newtons over here. That's my scale. Obviously, you're using a ruler when you're doing this. So that's 200 newtons here. And then 75, obviously there's like, there's 4 big boxes over here, means 200 newtons. So if I want to go for 75, it's going to be only up here. This is 75. So this is 75 newtons over here. Then finally, I connect them from the top all the way down over here. So you take a ruler, connect them up, and you use the scale and work out backwards. You'd actually find that this is going to be equal to 214 newtons. 214 newtons. and the angle which you're going to take out your protractor and measure it will be 21 degrees. Yeah, it's 4 easy marks here, but just make sure that you use the scale diagram to be able to do this. 8. A student made a moving coil loudspeaker. Figure 15 shows a diagram of the loudspeaker. What is the name of the effect used by the moving coil loudspeaker to produce the sound waves? What is the effect here? Well, don't forget you're using current and you've got a magnetic field and it causes motion, therefore it's the motor effect. It's the motor effect here. Not the generator effect, it's the motor effect. 8.2, explain how a moving coil loudspeaker produces a sound wave. Right, so how does this actually work? So how does this work here? Okay, so how does it actually work? I've got a whole video dedicated to that. You can actually watch that, but I'll just quickly do it right now. Number 1, you pass current through the wire. The current through the wire will generate its own magnetic field, which will interact with the permanent magnetic field over here. Both those fields interact, causing the cone to experience a force. It goes one way. Then when you reverse direction of the current, what happens is it attracts it back because you've swapped the direction of the field. That's the reason why. Watch that full video if you will need extra help, because this is a difficult topic here. But I'm going to put down the answer right now. So number 1, we're going to say current creates its own magnetic field. The magnetic field created interacts with the magnetic field from the permanent magnet, and therefore a force is experienced by the cone. And then when you reverse the direction of the current, the force moves in the opposite way. There you go, guys, the last point. When the current is reversed, the force is in the opposite direction. Don't forget, you must have the alternating current for it to move back and forth. Don't forget, it's a speaker cone. A student investigated how the loudness of sound from the loudspeaker depends on the number of turns on the coil and the frequency of the supply. As you can see over here, they are going to increase the number of turns and increase in the frequency. Explain why the results cannot be used to make a valid conclusion. Right. Hopefully you can see that, yes, the loudness is changing, but the problem is that they are changing the number of turns and the frequency. So that's the reason why it's not valid, because they're changing 2 variables at once. So if 2 variables are changed at the same time, the key thing from this is that obviously we can't see the effect of either of the variables. There we go. Impossible to state the effect of each variable, because obviously you change the number of turns and the frequency at the same time. 9. A teacher demonstrated how the magnetic field can cause a copper rod to accelerate. The teacher placed the copper rod on 2 brass rails in the magnetic field. The copper was able to move. Figure 16 shows the equipment used. Right, so you've got a power supply here. Current's going to go this way through the copper rod, down through the ammeter, through the variable resistor, and there's a switch over here. Don't forget the magnetic field is pointing downwards. The teacher closes the switch and the copper rod accelerates. Explain how Fleming's left-hand rule can be used to predict the direction in which the copper rod will move. Right, so look carefully. So take out your left hand for the left-hand rule. First of all, you should be able to identify that the Fleming's left-hand rule, the first thing you need to do is you need to obviously put your thumb, your index finger, and your second finger at 90 degrees to one another. Okay, so that's the first thing, and then you're obviously going to orientate it in the correct way for this diagram. So the current's going to go from the positive terminal, there, and then down through here, and then going like this. Right, okay, right. So obviously this is a 3D diagram, so you've got to now orientate your hand in the correct direction. So look, the current, which is going to be this finger, so this finger, the current, should be coming out of the page, yes, towards you. So you're going to put your second finger out of the page. So place second finger out of the page to represent the current. There we go. So represent the current direction. There we go. And the next one you're going to do is, which way is the field going? So don't forget, my field is going from north to the south, so downwards. So look, current coming towards us, field going downwards. So there we go. Place index finger downwards to represent the field direction. And then finally you can see your thumb will indicate the direction of the force. So thumb direction will indicate direction of the force. Therefore you can say the rod moves from left to right. There we go. And look at the diagram here. So look, if you go back to the diagram, it should make sense now. Look, current's coming towards us, field is downward, so therefore the force pushes this rod to the right over here and it rolls along. 9.2, so just 2 changes in the equipment that would increase the force. Right, look at the formula. We know that F is equal to BIL. So number 1, you can increase the current, so we can increase the current. Yes, we can increase the current in the circuit. And obviously the way you can increase the current is by reducing the resistance of the variable resistor. So you can obviously reduce this resistance here, therefore the current will be higher. The next thing you could also say is that you can use stronger magnets, so use stronger magnets. 9.3. The teacher closed the switch and the copper rod accelerated uniformly from rest at 0.15 seconds. The current in the copper rod was 1.7 amps. The mass of the copper rod is 4 grams. The length of the copper rod in the magnetic field is 0.05 meters. The magnetic flux density is 0.3 Tesla. Calculate the maximum possible velocity of the copper rod when it left the magnetic field. Right, so first of all, we know that the rod experiences a force, okay, and then that force will cause it to accelerate. And then obviously it will reach a final speed. So the first thing that I would do is work out what is the value of the force it experienced. Well, the force it experienced will be equal to BIL. F is equal to BIL, that's the force it is going to experience. So therefore it's going to be F is equal to 0.3 times by the current of 1.7 times by the length of the wire within the field, 0.05. I'm getting the force to be 0.0255 newtons. So that's the force. So you have the rod here and it gets a force of 0.0255 newtons. That's what its value is going to be. So, but now you know the force on it, but you have to work out the acceleration of it because you know it's going to start to move. Well, we can use Newton's second law, F is equal to ma, and we can work out the acceleration. So the acceleration is equal to F divided by m. The force we said was 0.0255. The mass that you've got is the mass of the copper rod. Don't forget it's the mass of the object itself, 4 grams, so therefore 0.004. Okay, and therefore it's going to be 6.375 meters per second squared. So that's the acceleration. So from rest, it will then start to accelerate. Now from here, calculate the maximum velocity. Therefore we can say that we want to work at the maximum velocity of it. We know that the initial velocity was 0. The acceleration is 6.375 meters per second squared. It's only going to be doing that for 0.15 seconds. So it's only going to accelerate for 0.15 seconds. So we've got the time is 0.15 seconds. The formula we can use, acceleration is equal to v minus u over t. The change in velocity divided by time taken. Rearrange that to make v the subject. So therefore, v is equal to u plus at. The value of u was 0. A was going to be 6.375. The value of t is 0.15. So 6.375 times by 0.15, I'm getting the value of 0.95625 meters per second. And that's it for another session of Ceerazzledazzle Physics. Make sure you try this paper yourself. Don't just watch me do it. Obviously, it helps to see what my thinking is, and hopefully I've explained it a bit better for you. Drop me some comments below if you're still getting stuck, and I'll try and get back to you as well. But good luck in your studies, guys. Ciao, ciao, and goodbye.